welcome everyone. Today we will be working on the iCEBreaker cube. Let me show you just on the desk. No, wrong desk, this desk. There we go. So what we will be working on is this wonderful piece of engineering. This is an LED cube that the 3D model is made by Bob Miller, or K-Bob. You can find him on Twitter. He spent a significant amount of time designing it. It uses 64 by 64 LED panels. This is something you can, in theory, buy off the shelf as part of a video wall display. So these are actually commodity items. The problem usually is that if you buy them from AliExpress or other websites, you have no idea what you will be getting, because even though they all look pretty much the same, this is what the tab is for, Bob. It's for opening the cube, because it's easier than jamming my fingernail in there. That's why the tab is in there. So anyways, let me tell this story. So the LED panels are something you can buy off the shelf. The problem is the circuit changes wildly. You will never be able to buy the same panels twice. They keep changing them. They use different driver chips, different shift registers, different row address chips. LEDs are also from different batches, different manufacturers. They have different color balance. So there's a lot of inconsistency if you decide to buy the panels from AliExpress. So I recommend, if you build a cube, buy at least a few extra panels to what you need. So don't buy 6, buy 9. Or 10 or 12, so that you have a bunch of spares that you, if any of them get damaged during transport, because that happens, the LEDs are quite fragile and they can break off in transport. And so you will want to replace them at some point, or you drop it on the floor or something. So that's the one solution. The other solution is we actually ordered a ton of the LED panels to spec with specific circuitry, so you can buy them from 1bit². We don't really make money on them. It's pretty much one-to-one buy, sell, wash. So you can find them on 1bit² if you want to build a cube. Anyways, so the cube itself is built out of modules. Bob did an amazing job of having as few fasteners as possible. Basically, just the outer structure is bolted together. You see bolts in here. You can screw it together. The whole frame is 3D printed. So you can 3D print this whole design and bolt it together. You will need some hardware like magnets and the electronics themselves, as well as wire harnesses, but we will get to that in a minute. So if you look inside, in here, there is a Raspberry Pi here. It's a Raspberry Pi 3, which is then connected over USB to the iCEBreaker, which is here. And it uses an LED panel driver PMOD to drive all the LED panels in one big string. Bob just posted the link to his repository where he describes all the parts of the design, including the power board, which is this board here. This is the power board. And the power board contains three things, essentially, or four rather. So it has the power supply for the Raspberry Pi, which is a relatively small switching 5-volt power supply, as well as a big 5-volt power supply for the LED panels. It, I think, is spec'd for 25 amps, 5 volts. We don't really need that much. It turns out we need, I don't know, up to 12 amps, maybe 13 amps for the LED panels when they are fully lit. but it's good to be safe than sorry. Also, this is the first, pretty much the first revision of the power board, so we didn't exactly know what we needed. So this was amazing job. 15 amps, 4 volts at max brightness. Yeah, that's good to have. Thank you, Bob, for the info. So this is also interesting. This is adjustable, so we can set it to lower voltage to use less power than the 5 volts, what the spec of the LED panel says. This is also an interesting topic because if you buy, depending on which panels you get, they can not work at 4 volts. Sometimes you need the 5 volts because otherwise the thresholds are not there. So, or you need to lower it because of other I/O voltage reasons. So it is all very dependent on the hardware you have. Also the structure on the back, so the 3D printed webs on Bob's design are made for this particular panels, with assuming that the parts are exactly in this position that you see here. So the power board was started by Bob, but designed by George Lokamides. He did an amazing job on the power supply board, so kudos to him. This board also, besides the power supplies, also contains an IMU, which is connected over I2C to the Raspberry Pi, as well as a soft power on/off button. So yeah, the Raspberry Pi takes power from the power board. It renders graphics, sends them over USB over FTDI to the FPGA on the iCEBreaker. This has a frame buffer in there. This in turn takes the frame buffer and displays it on the string of the LED. So currently we have only one string, so all 6 LED panels are in one big long string. The other also interesting thing is how they are being driven. Is these are 3 rows of so you have RGB shift registers that are then connected all through the LED panels, and we have 2 sets of the RGB shift registers, so we can light up 2 rows of each LED panel at the same time. That's it. We cannot light up more than that. So what has to happen is we have to shift in a color pattern, display it on one row, and then switch to the next row. So we have to scan like on a TV and go through the rows and display the graphics. Also, we don't have any grayscale control within the panels themselves. So what we have to do is do it ourselves. So for each bit of the color, we shift in the color for the least significant bit, let's say. We light up this row for a time unit of 1. Then we shift in another color set for bit more significant bit, so bit 2, display it for 2 times that period, then 4 times, 8 times, and so on. So as a sum, depending on which bits we're on for each color, we get a sum of time within the time frame or the frame time to be displayed. So this is very interesting how you don't PWM each LED, which would be very difficult, but you actually combine sets of like blips of different time that is always the square of the previous one, or 2 times the previous one, to create a sum of color. So we do that for each row, then we scan through the rows. All these things are done in the FPGA, so all the Raspberry Pi has to care about is to send the video frames to the iCEBreaker into its frame buffer, which is very nice. So yeah, let's, I think these are mainly the description of the cube, what it does, what it needs, and how it works. Let me just plug in the battery, which is this guy. This is 18650s. Inside are clipped in on springs, so there is a 3D printed spring here that you can compress, and and this will go inside the cube in its position and then lock in. My 3D print, it's like something I need to ask Bob at some point to get me a new set of those, because these over time softened and they are not holding the battery as well inside as they used to. So, and I don't have a 3D printer. This is something I have to solve eventually. Yeah, let me move this out of the way. Okay. So, if I can, this is a little bit finicky because it has like feet on the bottom. I have to slip it into. I marked them. There we go. 1 and 2. And there we go. Now it's locked in. And now we can plug in the power cord. Click. And power on. So you see it makes this blip of squares on the LEDs. This is actually generated by the iCEBreaker itself. If the iCEBreaker is not getting any video data in, it will time out and start displaying its own animation on the LED panels. And as soon as the Raspberry Pi, what you see here, starts rendering something, it will be displayed. The interesting thing is, as you see in the video, it's probably visible, you get those artifacts. If I have to see which, how can I show you the best? So you see the flickering on the LED panels. This is something I would like to address today, is to improve the situation of the scanning. You see those V-shaped scan lines that in the LED panels. So this is what is the scanning pattern causing. So the interesting side note is, if you were to just scan the display linearly, so from top to bottom, and do that in 2 rows. Oh, you see it now very well. It's like it's causing those chevrons. So these are the scan lines. So what is happening is we could scan just top down and then top down. What would happen though, if you have a sharp line, the sharp line would get tearing, especially with like normal perception with your eye, because the time difference between the top line being shown and the next line being shown is quite long, because it is the full frame time of the scanning. So what TNT, who designed the FPGA bitstream for this to drive the LED panels, so TNT, or Sylvain Manau, he designed the FPGA design. He came up with an idea that we could essentially scan first, last, and then basically go into the center. This way, the time difference between the top half and the bottom half is the smallest. So each 2 adjacent lines, their exposure time is as close as possible to each other. So that's why you get those chevrons. This makes a tearing of lines minimized. So that's a nice visual effect. So welcome, Tinkerled. So here, because I have a lot of background light and it is pretty matched with LEDs, the scanning is not as bad. Really, if you have a cell phone and people are trying to make photos of it when I bring it to some events, it is very often they have the issue of having really large scanning lines because their exposure time is very short. So this camera seems to be doing pretty well because it is stepping down the ISO quite low, and so it is exposing for a longer time so that this full scan is being visible. So for the low overall brightness displays, it is pretty good. For everything that is very bright and the camera would expose it for a shorter period of time, this will become an issue. So what I would like to do is improve two things today. So one thing is look into the FPGA design that TNT did and the changes that Bob did for the cube, and do two improvements. One is to decrease the delay between the no video displayed animations, because I find this, it looks like the battery ran out or something broke if the cube is all black for a very long period of time. So I would like to increase the frequency that the squares are being displayed when there's no video being fed into the iCEBreaker. The second thing I want to improve is actually the scanning speed. So I want to sacrifice overall brightness, and I will try to get into how it works and why we are losing brightness, but lose some brightness and increase the refresh rate. So to have a higher FPS on the strings. Besides doing it on just how what our time periods are, or the periods of exposure are, we could split the string of the LED panels into two. So have, instead of 6 panels in a string, have only 3 panels in a string. So 2 strings of 3 panels. This would increase the frame rate by 2, essentially. Or this is not actually exact, because this is the shifting speed multiplied. So instead of shifting in pixels at 30 megahertz, we would be shifting pixels in at essentially double that, so 60 megahertz. Or the bit rate would be higher, so we can have a higher frame rate. With the current hardware, with just the dual iCEBreaker LED PMOD, let me see if I have it here somewhere. Yeah, let me show this to you. So this is how it looks like. So we have this iCEBreaker. To focus here. Come on. There we go. So this is the iCEBreaker, and it has the dual PMOD connection here. And we have this converter that takes the 2 PMODs, sends them through 2 level shifters. So in the cube, and by default, the level shifters actually don't do anything. They are used as buffers to stabilize the I/O signal. Oh wow, that looks freaky in the background there. So they are wired to 3.3 volts, so they just serve as buffers. But you can also use the auxiliary 5-volt connection that allows you to step it up to the 5-volt I/O signaling, which the LED panels actually expect. So the requirement officially for the LED panels is to have 5-volt I/O signaling. But a lot of the panels can work on 3.3 volts. Again, it really depends on what you are getting. So this is how this looks, and what we would need to do to add an additional string of LEDs is double the RGB signal. So each half of the display is getting 1 red, 1 green, 1 blue. So there are 6 RGB per string of the panel. So if we wanted to add a second string of the LEDs, we would need to get an additional 6 GPIO, which would be possible if we also tapped into this additional PMOD. And then we could drive 2 strings of LED panels pretty easily. For that, I was thinking maybe we should start designing hats for the iCEBreaker that essentially takes the PMODs and plugs in on top of it, so that we can do a higher GPIO count well, not PMODs anymore, ice hats, or I don't know. We should come up with some good name for how to call the modules that are for the iCEBreaker. So that's the idea for hardware design that we can come to at some point. I am a little bit concerned with the cube. We probably can't retrofit it easily if I had double strings, because the iCEBreaker, if you look into the 3D model, is tucked in under the power board quite tightly. So I'm not sure. We could do that. Oh, welcome, Art Sale. So the question is, how many bits are you using now? I have no idea what the color resolution is, the default one. We will see that in the config. If I think this is part of the columns, channels, planes. So this is at 10-bit per color. So there are 10 planes at the moment. So bit depth is 16. So we have eight colors. Yeah, so we have 16 bits. So 565 as data input into the iCEBreaker. But the iCEBreaker itself does gamma correction. So it converts the 5 or 6 bits of each color to a 10-bit deep resolution of color. So it is. We have for each grayscale there's 10 bit planes. That's at least according to the configuration that I see here for the bit stream. So Sylvain did make built-in gamma correction into the iCEBreaker, so you don't have to deal with it, which is pretty cool. Okay, where were we? So yeah, let's. If there are no more questions, so one more thing as a side note for the streaming. After the last stream, I finally became an affiliate of Twitch. So finally we get all the funny things like channel points and subs. So feel free to play with that stuff. So let's go to the desktop here. So the two things that I wanted to fix or change is, first of all, increase the frequency of how the squares are being displayed. So let me maybe log in first to show you what I'm talking about. So yeah, I think this disconnected. Yeah, I had to change the battery while so we can like this. Yeah, so now it should, yeah, there we go. So it is displaying the squares, and it takes quite a while for the square to show up again. So I don't know. I basically, when there's no video being displayed, I don't know what state the thing is in. Did the Raspberry Pi crash? Did the power run out in the battery? What is the problem that it is staying dark? So I want to just show the pulsating squares at a fairly frequent manner, so they are displaying all the time while there's no video being displayed. So the same thing happens when you power it on and the Raspberry Pi has not booted yet. So we basically get that. Decreasing the bit depth might increase the frame rate, but it is not exactly twice as fast, because this is the complicated part. Intuitively, you would shift in all the pixels, switch on that row, and shift in the next set of values in, and use that as your baseline for how long the smallest chunk of time you would use for the color, for the grayscale. That's the intuitive thing to do. But then you would get a atrocious frame rate. So you would really get a really slow frame rate. So basically you would shift in first the pixels. So let's say 64 pixels, shift in 64 pixels, display it while you're shifting the next 64 pixels in. So that would be one time frame, and then twice would be 2 shift times, would be the second bit, 4 shift times, and so on and so forth. So you would get shift time and longer gaps between it where you're not shifting. So what you actually do is you shift in the first pixels, display it, and you don't display that yet. You display it only for a fraction of the shift time. So when the next pixels are shifted in, so the next time, you're showing it for twice as long, and you create dark times that cannot be filled with display. So you lose light efficiency, so you lose light. So you create hard blocks of darkness that you cannot display anything. This way, you can have very short, least significant bit times. And so you pack in the shift times all together, or more and more of them together, until you exceed with your show time the shift time. And then you start creating gaps between the shifts. So I hope that makes sense. This way you can get a higher frame rate with packing all. So you essentially, if you went all the way and said it's like light efficiency is the least important thing to me, and you wanted the highest frame rate, you would say, what is my bit depth? And multiply it by the shift time of all the LEDs, add that together. That would be your highest frame rate for a certain specific bit depth. So it is all interdependent, how long you display things, and yeah. Yeah, I know. I already found where that was before the stream. Thank you, Bob. Yeah. So let's see. So I killed this, and we can go because we will have to go here, because the nice thing is we can synthesize the bitstream for the iCEBreaker on the cube in a pinch. So I have the repos and then ice40. So it is here, and I can synthesize this. And I did synthesize this on the Raspberry Pi, but it takes quite a while. So I'm not doing it. I will actually synthesize on the laptop and then SCP the bitstream onto the cube. That should be faster for the purposes of the stream. Okay, so there's RGB panel bin, and yeah, so now let's go to here, and what Bob was talking about, this is the place where we will change the full square burst time frame. So there are 2 parameters, T and T2. T is the rate the animation is being done, so how fast the squares are being are collapsing together, which is nice. I think this time is pretty good, and I think we will drop this to something like 7. Let's try 7. Save that, and this is the time between the frames. And then we are already here in the design. So I can build this. This is then synthesizing. In the make files, I think we should also put more of the output into log files instead of just printing everything onto the screen. That would improve. I'm really curious how long it will take when I'm streaming and using the CPU for other things at the same time. So yeah, this is synthesizing. The design itself doesn't take too much space. We can see that in a minute. So this is now routing, doing routing. I think the resources used is up here. Yeah, there it is. So it only uses 21% of the LUTs on the iCE40, and it uses 21 of the 30B RAM blocks and 22 I/O. So we still have some I/O available if we want to. Not heap. Oh yeah, I think heap is not enabled. It's possible that the heap is not, unless it's because didn't Dave? Yeah. Anyways, we can look into the makefile, but that's wasn't the heap placer. I thought it was using both, using the one first and the other later. That's the routing. Slack histogram. Oh, it is using the annealing. Yeah, it is not using the heap at all, is it? Yeah. Anyways, we are getting into the weeds of the open tools. So let me copy over the bin file, and then let's do. Oh, I don't have. Why is the iCEBreaker not in my path? Oh, because I switched over to Z shell on the iCEBreaker, and it doesn't have the bash path stuff. Aha! Trying to make my environment more mine. And then I'm losing. Where did Bob add the paths for the toolchain? Is it SFT? Yeah. Let's do that. Let's do this. Okay. Okay, let's see. Is it faster now? Yep, that's much faster. Do we want to make them twice as fast? Would probably be. Let's try one faster. This is pretty good, I think, but let's try it nonetheless just to see. So let's do 6. So by the way, the software that I'm using here, so the design, I was thinking about, okay, GitHub, Esden, iCE40 Playground, and I took, oh, George, welcome. Thank you for the subscription. So it is in a branch. It's the topic cube, which is a rebased branch from Bob's. So it is rebased on top of master now. So these are Bob's commits that he made for the cube in his repository, in his fork of the Ice40 playground, and I made some changes. So you can find it on my repo. So I will just paste it here into the chat. There you go. Thank you, George. Yeah, you made an account just for me on Twitch. Yeah, thank you so much. Well, now you can hear when I run another stream to praise your power supply design skills. So yeah, it's worth it, I hope. Okay, so that should have synthesized by now. So we can copy this over and then program it. Okay. Yeah, this is pretty good. This is pretty much non-stop now. So when it is booting, it would be doing this all the time. So yeah, let's see, should I? Yeah, I will commit this. This is just yeah. Speed up or shorten the dark time between how do we call it? Pattern. How do we call all of these things? Because this is the pattern generator for no stream data. Pattern generator for no stream data indicator or something. Maybe we should just call it regarding this square burst, decrease blank time in square burst. Maybe that's the word. Interburst or decreased interburst blank time. Dead time? Yeah, dead time is not bad. Thanks, Silva. Okay. All right. So that's pushed. So next thing is, so for our frame rate, so we can now start actually cycle, export path. I will have to add that after the stream because bin should be in there too. $. Ah, come on. So cycle is the script. Just do this. Okay. Yeah, so it does work, and it will be indicating when we restart the cube. It should also be displaying it. So now we should try to increase the frame rate. So let's look into that. The cool thing is that Sylvain added a calculator for frame rates. So there is a script somewhere in software. Stream control, no. There is a script somewhere that allows you to calculate the frame time. It was somewhere in here. Clocks pi, RTL, no. Where did that? It's in the course. Okay. Course. Hub 75 software. It's in here. So this is the timing. So this script can help you calculate the frequency and whatnot. So let's see what the current setting is. So we are using a single 2, n blanks is single 2x. Single 2x, that is for the PMOD that is connecting only to one output, or one PMOD, the single PMOD one. So I think the n blanks is 2. Frequency should be two, then n rows is 32, I'm pretty sure, yeah. Then we have n calls, and this is the really long one. This is 64 times 6, which is how much? Banks. Ach, banks. Thank you. Yes, 2 banks. Not 2 blanks. Okay, yeah, 2 banks. Rows. Banks, rows, columns is 64, 128, 384. Thank you. Having a remote calculator, that's awesome. Thank you. And then n planes, and I think this was 10 in here, correct? Yes. So let's see. So this allows us to see BCM LSB length, so least significant bit length. What is it currently? Inactivity time, bit depth, channels. It's not in here. Oh, it's in the lower. And banks. Let me just find it. BCM bit length. It's lower? Wait. Oh, it's a port. It's runtime configurable. So is that in the streamer? The streamer can set this? If it is runtime configurable? Because this is the least significant bit time frame, right? So if we crank it up, so light efficient. So this is the interesting part for now. Depending on what the shortest time for the display is, and it's basically, is it, I think it is the multiple of the 30 megahertz of the shift time. Excuse me, what? Okay. Oh, here in the project it's hard-coded. Okay, thank you, Sylvain, for clarifying all this. So it is a runtime configurable, it's a port, but it is not externally, it's still hard-coded at the moment. Okay, that's fine. And the CFG BCM bit len needs to be set to the value you want -2. So it can be, okay. But let me just explain what these numbers mean here. So we have the minimum bit, and I think this is in the 30 megahertz time frame. So how fast we can clock things, or is it something along those lines, right? So if you want the BCM LSB LAN 8 from the timing script, you set the CFG to 6. Okay, so let's see. BCM bitlen. Ah, okay. All right. So this is the value that we are looking here for. So this is the value, BCM bit length, which is 12. Oh, welcome to the stream. Thank you for joining. So we will have to, these are the numbers for our frame rate. So if I want, what I would love to increase is we currently have a frame rate around 60 FPS. And this is interfering with cell phones and stuff. So we would like to crank it up maybe even to 5, which is 70% light efficiency. So only 70% of the so let's assume we have non-stop this lit, and we are showing it at the maximum possible amount of time. So we can, if the LED is lit up 100%, it is lit all the time, like 100% of the time. Of course, there's like times transitions between shifting and stuff, but like let's think about this in the terms of what theoretically is possible. So that would be 100%, and 70% is 70% of the theoretical maximum time the LED can be lit. So we are losing maximum light efficiency. So I will try to crank it up probably to like 120 frames per second, and see if that that is possible. So that would be 5. So it is 5 minus 2, so it is 3. So we should set it to 3. Let's see if that works. Oh, there's a one-liner to do. Make the cube all white. That might be useful. Thank you, Bob. Ah, shader box. Okay, yeah. Let's see. How blindingly white is it? Yeah. So now it is just a square. Let's make sure I copied the right thing. Will that work? Oh, I have to do this. Copy pasta problems. There we go. Let's see. Donk! Ah! That is bright. That is very bright. Thanks, Bob. And there you go. And then now it's off. Okay, cool. Cool. Now we have a tester. But this way we can really see the scanning lines. So yeah, it's flickering like crazy. And it's very bright in person. Okay, so let's add here another comment and call it that would be number 3, and this would be 129.9 129.9 FPS. Let's see if that works. I should change back to the other directory. Make. Yeah, I can imagine that the streaming Streaming compression artifacts are even worse. Sorry about that. But at least I don't have one big tooth, do I? I hope. So by the way, Kate Temkin did an amazing stream yesterday. So if you're interested in all this FPGA awesomeness, definitely check Kate Temkin, the error that everyone makes, on Twitch or Mixer. You can also find her on Twitter, and there's a link to her channel. So if someone wants to drop in a link to Kate's Twitch, that would be great in the chat. Okay, so that's copied. Let's SCP this. Welcome to this stream, Babint. Thank you very much for subscribing. So, where's my SCP? Okay. Let's copy it over, and now let's load it and see how that looks. Oof, it's much faster. Right. It also increases the speed of the idle animation. That makes sense, because it's tied to the frame rate. Now let's make it white. Yeah, we still have a little bit of chevroning happening, but it's definitely way better. Wow. Let's see how that in person I'm trying to see. It's definitely better. It's much less flickery. That's nice. Imagine we did that with 2 strings of LED panels too. Oh, that's exciting. Okay, let's still try. This is still very bright. So by the way, even the 70%. So let's try doing it, going completely crazy. Hello. Okay, so let's, it's very fast. Okay, let's decrease. This should be dependent on something else, I think, the frame rate. Shining off my face, yeah, it's bright, very bright. And I have video lights here, so yeah. So let's do, we might want to decrease, can we, if we do this, 4? This is 1/4 of the speed. We increase the frame rate by 2. So let's do this. Let's decrease the square frame rate. FF is going as fast as possible. Okay. But this is already a huge improvement to double the frame rate to 120 FPS. It is not as shimmery as it was before. So that's very exciting. Ah, much better. Yeah, I think I might slow it down even a little bit more for the squares, but that's not the main thing why we are here. Let's do, so you said, so we have, let's try FF. Why is it doing this? Oh, it's in D, so we should do H, X, FF. So that would be the maximum. So that's the shortest time possible, right? I assume. Which would be, from the calculator standpoint, So let's look at that. So -2, yeah, so it wraps around. That's interesting. So that would be 233 FPS, which is pretty nice. Yeah, let's do that. Let's try it. Let's synthesize this. I have to, yeah, make. There we go. So this is pretty decent. Still, the synthesis time I find fairly reasonable here. But I'm pretty sure, I think we might want to adjust the makefile to also do heap. I have the feeling this is just not enabled, because I think this was an additional parameter in the makefile. Might be disabled specifically or something, but we can look into that in a minute. Why it is not using heap. Okay, let's see. That's definitely fast. Yeah, that's, I do definitely see that it is not as bright as it was before. It's still pretty bright. Does it light me up still? It's definitely not as bright, but it's not bad. And it's pretty solid, isn't it? Oh wow, I'm glitching out the camera here. What the hell? Wow. I'm managing to glitch out the Logitech camera somehow. Wow. Poor camera. So let's just run the cycle. Let's see how that looks. It's not bad. I think this is too much though. This is not as bright as I wish it was. I think I want it a little bit brighter than this. But it is nice and smooth. No, it's definitely nice and smooth. Less bright, and so the exposure is longer. Refresh faster. Yeah. Yeah. Still, does it freak out this? This doesn't. Yeah, it does freak out the camera. Oh my god, it's breaking it up. Is that EMF? Is that the switching power supply freaking out the camera? Wow, that is impressive. I think I should measure some EMI on this thing. I have the feeling this is spewing a bit. That's fun. Okay, so I think I do want to, let's crank it up. Let's see, what was the difference? It was 25%. 25%, 43 is double. So yeah, if I go just to 0, so aka 2 BCM LSB lens 0, then I still get 200 FPS. Yeah. What might be useful is actually, so to synchronize it with the power grid, so actually have exact 60 FPS. George, yeah, I know. I am throwing shade on you here. I'm blaming you that my camera is freaking out. Yeah, 1 should be reasonable. Okay, so yeah, crank it up to 60 hertz. 172. Yeah, that's the point I was trying to make. If we can actually hit almost exactly 60 FPS, then the scan time of video should be also much more reasonable. So yeah, let's do that. So it is a 1. Yeah, a 1. 0, 1. Let's do that. And I'm pretty sure it is the power output on this guy is, I'm sure, very good. On the power supply, this is not a dirty power supply output. I think I would assume that the inductors or something are producing some signal. So that's why I'm saying I should do some EMI measurements if I had the tools for it. Right, so it is an approximate. I think it would be nice to actually hook up a logic analyzer to this and measure the exact frame times. That would be fun. Then we could also do things like adding delays to this, so actually hit exactly 60 FPS to synchronize it with the grid, and then have two versions for traveling to Europe and running on 50, so having a multiple of 50 hertz, and here in the US having a multiple of 60 hertz. Because I know cameras are actually switching, if you like cell phones especially, you go to Europe and it switches over to 25 or 50 or 100. And you are here in the US and it does some multiple or divisor of 60, which is interesting. So cameras do pay attention to this. There we go. Let's do white. Fonk. Yeah, we have some wandering chevrons a little bit in the camera, but it's not bad. Let's see how it looks in person. This is pretty good. This is not weird. It was definitely weird before. Okay, this is also nice and bright. This is nice, I like it. It has a, not sure how that looks if you see it on video, but it definitely throws a nice light onto the table. Let's do cycle. Yeah, it will slow down the squares a tiny bit still. This is neat. Yeah, no, the brightness is much better now. It's a good compromise, I think. It was a little bit too dark before. That's very cool. There we go. It's mesmerizing. Okay. So let's also adjust this. Let's slow it down maybe another half. Yeah, I didn't see square bursts added to the upstream yet. But I did rebase your stuff, Bob, onto Sylvan's master. So I hope I didn't break too much. Okay, still running. I think it has to be killed separately. Where do I have it? Server FPGA. There we go. Now it's dead. Welcome to the stream. Thank you for subscribing. Yeah, so there is also Breakup 3D. There we go. Now it's dead. Now we can do iCEBreaker. iCEBreaker. Let's see how the squares are doing. Oop, that's not good. There we go, that's better. What? Oh, is it slower than the dead time? Okay. All right. That was not good enough. What did I decrease it from? Let's do 7. Synthesize. Yeah, I really want to get a dedicated machine for all the on-stream programming and synthesizing whatnot. It would be really nice. This old laptop is not the fastest. It's still very fast if you think about it. It's at least not minutes and minutes of Vivado synthesizing stuff. On this machine, definitely, but this machine is very slow, so it wouldn't be that fast, I think. So let's try that. There we go. Oh, it is still cutting it off. Just slightly. But it doesn't look bad. But I don't want it to cut it off, so let's do 8. But the speed is good. Oh, you missed it first time? Okay, so it is using keep. Good. So we can see more than one side. Okay. There you go. Better? Yeah. It's not bad. I like the pulsating. But it shouldn't cut it off. I think it will be better when it has some blank time between. It's not bad though. I like it. It's a nice animation. And copied. Let's try it again. Yeah, that's good. It's not long enough to become weird. Yeah, I think that's good. I'm happy with it. Let's see. Let's commit this. I think we are good. So we should also add the 1 and then the frame rate, right, in the comment. What was it? It was 172 something. There we go. This was 172.8. One results in FPS. That should be good. Okay. Let's add a space here. I like it. Oh, we should also add here, make it nice and visually aligned. Okay. So that is, so the frame rate will be a little bit lower than the 172.8. So it will be in the vicinity of 60, a multiple of 60 FPS. It looks better on video? Okay, cool. Cool, I'm glad. Okay, that's, then we have a success. Yeah, the main thing of this exercise, so it was looking a little bit weird when you were moving it with your eyes, but it's not terrible. The biggest problem we had was everyone who was trying to photograph this had problems with capturing how the cube looks. Everyone was seeing the scan line. So this is the main reason why we are doing this. Okay. Let's see, git diff, and then we added this, and we decreased the BCM bit length, and that looks good. Oh, thank you for a bit. Thank you so much. Let's see, what is the commit? Yeah, let's call it decreased LSB exposure time to trade new cube frame rate is 127, right? 172, sorry, 72.8 or 72 FPS, and let's do it approximately. Push Esden topic cube. There we go. So that's done. So that's the project for today. Wow, that went much faster than I thought. But what we could do is look at some other software that is running on the cube and maybe update some of that. So the first thing that is running on here is the server, so the cube server. So to explain what it is, there is a project Squawave dot, which is a project that all of this cube stuff got inspired by. And it's a project by good friends who I saw at the Congress for the first time several years ago now. So they created this LED cube using 2.5 millimeter pitch LED panels. We have some here actually. So they are a little bit bigger than what you see here. So yeah, for comparison, these are the bigger panels. So they are 25% bigger. Is that comparable here somehow? So the cube becomes slightly larger, a little bit more difficult to transport, but it is still a very nice size. And so this is the LED panels they used for their cube. And this is what I saw about now, 2 years ago at CCC. And that was part of the inspiration why this cube even exists. is the square wave dot people. And they are working towards having a campaign for their cube, which uses injection molded internal structure. And but it is going back and forth. This is the nice thing about this. They share their software open source. They publish that, as well as they then incorporated some of our hardware changes, like the FPGA, into their own design, which is very nice. This is a cross-pollination and back and forth between projects. So their cube looks very nice. So check it out. Yeah, there are some photos of them building the internal structure. So you see they have a injection molded case on the inside. As you might see, the effect is the breakout game that is on here is part of their software stack, and I would like to update it because they also support the IMU being read out, and you can play with that. I just have to, and I saw the newer version of their software at CCC this year, and that was very, very cool. And yeah, I should update that. I'm trying to figure out where it could be on there, because Shader Boy is Bob's OpenGL rendering engine that uses the shader toy scripting language. So Squarewave, I think they're using a different IMU, but I'm not sure. Repos, oh yeah. Thank you, Bob. Cube shaders, and there's Matrix server, there we go. Reuse address. What did you do here? TIG, let's look. So Bob added something. So reuse address to the TCP server. Interesting. So we might need to do that. Okay. A remote. So we have just the original squarewave dot thing. Wow, that stuff happened. Adrian, there we go. So let's, oh, come on. What happens if I do this? Oh, this is not on this. Oh, it's on the Raspberry Pi. I will not be able to open that. Okay, the Sublime merge is not installed on there, obviously, because I don't have a GUI. Let's just do this. And so ADS 1000, is that the IMU? I would think so. Oh no, MPU 6050. I don't know what we put in here. Is that the MPU that is mounted on the power board? I don't remember. But we can example applications, breakout, cube test, generic. There are some examples, but I think they had more animations in there. But maybe it's in their private repository, I'm not sure. I would have to ask Adrian what the status of the software was. But we can probably build it. What does update sh do? Matrix server releases. Huh, you can update it as Debian packages. Interesting. From the GitHub repository. Huh, cool. Let's just build it, I guess. Check build system, failed. Huh, file provided. Thank you for joining. Welcome. Fetch origin. Submodule. Let's see if there are any submodules. No, there is not, but could not find package configuration file provided by matrix application. So find matrix application. Maybe I should just do this CMake rebuild. Let's look at the README. What do they say in here? Build CMake, cd build CMake dot make. Okay, yeah, that's it. I can't find it. Come on. Main menu. So something is broken. Matrix application provides separate development package or SDK. God, okay. GitHub. Do they say update? It's square wave dot and then matrix server. Square wave dot matrix server. What repositories do they have in here? Example applications. So this is separate now. I think they moved it out, most of it. There's a web UI too. Ah, this is where the applications are. Breakout 3D. Yeah, so there's... I need to clear the repo. Okay, fine. Oh, it's 9250. Okay, so it is a different MPU version that we have in our cube. So we might need to make a new driver for it. Okay. Let's do this. Let's rebuild this. Oh yeah, you are right. Oh, it still complains. Protobuf. Find matrix application. Yeah, I don't feel like debugging this now. All right, well, I think that will be it, because I don't feel like debugging this kind of stuff on stream. This seems like a little bit silly and boring. So yeah, at least we managed to do the frame rate improvements, and I pushed that. I hope we can merge this upstream with Sylvain's design. Let's just run cycle in the meantime. So this stream was a little bit shorter than usual. Why is it not starting? Are we occupying the USB port? Yeah, I think something is happening here. Let's reboot this thing. I hope this will restart and then run. Yeah, it was not. So yeah, I erased the build dir and it was running from there. Yes, I did try that. I will play with it off stream later and try to fix it and try to compile the newer version of the firmware. Also, I have to figure out where the demo applications are. So this is something probably for the weekend. Yeah, I'm confused why this is not starting the animation, even though I rebooted it. Let's stop it. Okay, this is powered off. Let's power it on again. Did I break the bitstream now? Still booting. Come on, you can do it. Okay, well, we will see if this starts, and if not, I will probably look into seeing what I did to the bitstream or something. I'm curious what could have happened. Has the build directory hard-coded in it? Oh, great. Okay. Yeah, so it is not cycling because the server is not in there. Okay. That's a good point. So let's fix that part by removing it from the cycle script first. Let's just disable it for now. Yeah, see, it's like it was running. Hey, welcome, I see you, boy. Welcome to the stream. So I will just disable this and pixel flow and the sleep 30. Okay. Yeah, so basically I broke it completely now. So the server from the SquareWave guys definitely didn't work. So I have to fix this. Oh, thank you for subscribing. Thank you, iCEBreaker, and welcome. So the animations where the frameworks we currently actually have running, which I didn't really talk about. Because there are multiple frameworks that actually work on the cube. One of them is, oh, I should disable breakout too. So it is basically just showing nothing for a minute and then going to the other animations. So Shader Boy, GL test is one. Then we have Shader Boy. Shader Boy, I think after Bob updated things, because this was me updating things based on his. We don't have a central repository for the software yet. We don't have like a Raspberry Pi distribution that we use, and this is why I am doing some changes that are not the same ones as on Bob's cube. So currently there are, I think, only 2 of this setup. So Bob has one and I have one. I don't know if Sylvain actually built one of these cubes too or not, or if we have other people using this kind of setup. So what I did is after Bob created the Shader Boy, which is playing the Shader Toy language. Oh my God, this is such similar names and really difficult to keep track of. So Shader Toy is a web-based OpenGL animation website, so you can live code animations that are OpenGL. I hope this will not crash my computer, because this is using WebGL. And this WebGL stuff has a scripting language, which is essentially a shader language, scripting language. And Bob created a C application that can play very similar scripts. Yeah, thank you. I'm glad you like it. It was a huge group effort. There's a lot of people involved in this. So then I added it to my setup and what Bob created. So we have Shader Boy, and it is going through all the demos inside the Shader Boy shader repository. So now that I think about this, one thing I should do is disable the Shader Boy animations that are somewhat broken. I don't know if they are broken or not, but they were causing some issues. They created like one of them is just making it white, and one of them is making it crashed previously for me, so it was always black for a while, and then blinding everyone with a white screen. So we should probably disable that on the cube. But yeah, Shader Boy is one of them. Then we have also SLED. SLED, the framework, is really awesome. So this is from God, how do I Shiny Blink, there we go. Okay, so the group is called Shiny Blink. It's run by Vifino, and they basically got a lot of LED panels and started bringing it to different hacker conferences. And the idea was they wanted something super simple where people can contribute their own effects to. So what he chose is a Just C and a frame buffer, so you can very simply write your own effects for it. These are just object files that it loads. So if we go in source, we have a lot of modules, and I think it is in here. Yeah, and these are different animations, and it randomly chooses them and displays them on the cube. So what you're seeing here, these pixely animations now, for example, are from SLED, and there is a ton of different effects. People now added a terminal mode, so they are doing like really tiny font terminal animations on it too. So this is just assuming the cube is a flat 3x2 LED panel display, and this is what we are displaying on it. It still looks very cool, even though it is not completely like fitting together, and it is not really aware that it is a cube. But Shader Toy is really awesome, and it has support for the streaming protocol that we use for the iCEBreaker. So you can use SLED just with an iCEBreaker and LED panels. So yeah, what is happening now? That was cool. That was resetting. That was interesting. Will it go back? Yeah, the transitions between the different effects are interesting sometimes. Oh yeah, because I disabled it. Ah, right. So what I did is I disabled the script, so there was no new animation running afterwards. Yeah, the SPI did something, but it didn't actually send it. That's cool. Oh, yeah. It's every time. This is why never touch the cube at a conference. Don't try to improve or fix things while you're on a conference. You will break it. I did. It took me hours to fix it once. It was so bad. It was, I think, B-Sides PDX, and I thought, oh, while I'm here, I can sit here for half an hour and like add an effect or like fix something. I don't remember exactly what I wanted to do. So I pulled out the SD card, put it into my laptop, added the Wi-Fi network that I had locally to the Raspberry Pi, and then I put it back into the Cube and it doesn't even boot anymore. So that was fun. So the problem was, it turns out, that it was not booting because for some reason me changing the WPA supplicant config file made the file owned by someone else. So basically it didn't have access to the file, and then it was crashing. So I had to pull out the Raspberry Pi, find a USB to serial adapter, connect that to the Raspberry Pi, connect to the serial console, go into the shadow file or something, and like touch the files so that it is owned by the right person, then put it all back together. Oh my God. I spent 2 hours not fixing what I wanted to fix, but fixing what I broke trying to fix things. Yay, fix inception. So yeah, from now on, I'm only making modifications and changes when I'm at home, in the worst case scenario here on stream. But yeah, it's bad. All right. It is interesting. It does make some... I think it is because we increased the frame rate. We see things that I didn't see before. Come on. Oh. Let's see. Kill. Okay. So now we killed the cycle because this was running from the bootloader. Now we can go to repos, and then we have cube shaders, and we want to actually go to shader toy, shady. Which one is it? Cube shaders? There's like cube shaders, LED cube, shady. Is shady old? Because there was an old repository too. Shady? No, that's Polyfloyd's shady. So that's Polyfloyd's framework that we are not running on here, but it's another really awesome OpenGL-based framework for cubes. Then cube shaders, what do we have here? This is also Polyfloyd's. Yeah, GLSL. George, are your days just fixing things that you wanted to fix but broke in the process? Yeah, I'm sorry, that's horrible. I am looking for your shader boy thing. That's what I'm looking for, Bob. Is that in the top level there? Yeah, there is shader boy. It's on the top level directory, not in the repos subdirectory. Why is it all over the place, Bob? Okay, that's it. So, shaders. See? Lip shade, shaders. Shader box, right? Shader box. Let me see. How does this started? Bin cycle. Oh, it was me. No, you are not the messy person. I'm the messy person. I cloned that directory in there, I'm pretty sure, instead of putting it into the repos. I'm a messy person. I didn't know what your organization of directories was on there. I'm pretty sure it is my own fault. So yeah, so oh, come on, wake up, figure it out. Shader boy, git, shaders, demo, and then shader box duration 10. Okay. So shader box is installed in path. So shader box So let's try blocks. Block is fine. So this is the alphabet block. That looks nice. Man, this was so flickery before we made the speed changes. This is so much nicer now. I'm glad we did this fix. Okay. Then we have conic should work. So I probably should just... This one has like a flicker to it. Yeah, it's breaking up here. This is weird. What's happening here? Is the frame time, is it taking longer to shift the data in now than the cube needs it? Are we getting screen tearing or something? Yeah, this looks weird here. Is that visible on stream? Yeah, I think it is. Yeah, you see it at least on the video here. That's weird. Okay, we will have to look into that. Well, that is. But at least it works. I will create a shader selection. And then copy block to shader selection. Then copy conic to shader selection. Oh, I need to copy the alphabet probably into there. Pragma map alphabet emit alphabet. So yeah, it is using this. Okay. Yep, thank you, Bob. I did copy it over, thanks. Okay, so next one is Curve Wobbler. Let's try that one out. Yeah, that's nice. It's the Curve Wobbler. Okay. I will make a very short pause and come back in a second. We will finish just checking all these and selecting those that work well. I might also make a poll here to see if there are any updates from Bob. But otherwise, yeah, I'll be right back. Just give me a second. All right, I'm back. Sorry about that. Okay, so we were choosing some of the shaders into our shader selection. So let's finish doing that. So Curve Wobbler was good. And what else? Next one is Filling Tiles 3D. Does this work? Yep, that's Filling Tiles. That's a nice one. And then MB. That looks good. I'm really curious which one was the one that was causing issues. Are there any updates? Let's check that. No, we are up to date. Okay, so the shader box is up to date, or the shader boy. Okay, MB, and then Munch 0. These are very nice. Yeah, I love those. These are really pretty. Yeah, very mesmerizing. What do you guys say? Isn't that pretty? It's a signature animation from Bob, the Munching Square based animations. Signature Bob. Shader selection. Then I know that the Munch one is also really nice because it has also movement. It like rotates. It looks like a kaleidoscope. Okay, Git remotes. It should be GitHub Kbob Shader Boy. Yeah, it is. TIG, yeah, what are the changes? Master, adding missing shaders, Curve Wobbler, and Verneuil. Yeah. Okay, so next one, we had Munch. So let's look at what else. We have RGB, which is just this, which is really nice. It's an RGB cube. That is very nice. Very neat. That one stays. Smiley, and we need to copy the smiley PNG. I'm pretty sure that's the smiley. There we go. Very nice. I should have just copied the whole directory and deleted what I need to delete if I need to delete something. Yeah. I know. Why do it simple way if you can do it complicated way? We are all more than half through, so let's keep going. Yeah, this one doesn't work. So smooth Verneuil contours is broken. Oh, there we go. It's causing OpenGL errors. Huh. Okay, this is what it was. What was the problem? So if it is running on this effect, if I run it just randomly, it was causing exactly that. It was staying black for a while and then blinding everyone with white. So that's probably what it is. It's the OpenGL error. So we are not copying this one. So let's for a short break here. So Marshall, thank you so much that you got an icebreaker. I hope you have fun with it. First of all, where to get started? Well, there's the icebreaker workshop that you can find in the organization. There is a WTFPGA workshop. There are a lot of examples in the repository, so I recommend that you oh, it is too compute intensive. Okay, now I understand. Thank you, Bob. So regarding resources, follow Kate Temkin. She's streaming about learning about FPGA. She's working on a course based using the icebreaker as the target. Yeah, so we have a lot of examples at the moment, and if you just learn Verilog in general, if you take, someone posted in the chat earlier, Kate Temkin, I will show you the link. K Temkin, that's the Twitch channel. Let me just copy it over for you. So, so this is her channel. I recommend following her. She's also on Twitter under the same name, and Matrix the same name, and YouTube the same name. So this is good resource. And then yeah, as I said, GitHub, iCEBreaker, FPGA. There are multiple repositories. We have icebreaker examples for Verilog, MyGen, NMyGen, and iStudio. iStudio is a very good platform to play around with FPGA. We have the WTFPGA workshop. That's one resource to learn just the basics. And then we have the icebreaker workshop here. This is something we did at the Congress this year. So there is a PDF that you follow the instructions in, and that is something I can recommend too. So that might be a way to get started with the icebreaker. Yeah, I hope that helps. And thank you for joining the stream. I will definitely be doing more content regarding FPGA programming or FPGA development in here. So stay tuned for that. Okay, so let's go back to us trying out the different GLSL effects. Yeah, so yeah, you're welcome. Well, it's not the 1-bit squared GitHub directly. We also have an org for 1-bit squared, but and the icebreaker FPGA is the correct GitHub. Wait a second, what did I do here? I meant to go GitHub, icebreaker FPGA. That's the link that you would want. Let me copy that in here. There you go. So that would be the organization that you want for icebreaker related stuff. Okay, so where were we? We were Shaderbox, and then V. Is that a working one? That is the Verneuil, I guess. Are they two Verneuils? There's V and Verneuil. What? Voronoi. Peter. Yeah. Do they differ? No, they are the same files. Huh, interesting. So we just copy Voronoi then, because otherwise it's running twice, I guess. That's what I also saw, that it was running twice during in the demo. Selection. So let's copy that. Then bin cycle, and then change the directory from shaders to shader selection. Right? Shaders, shader selection. Okay, so let's run cycle. Let's see. So that should work now. It shouldn't crash anymore. One of the Bob, are you messy? Maybe? Well, we can clean this up. It's not a big deal. Yeah, we should definitely delete the one that is not meant for Shader Boy, because if we have effects in there that just don't work on here, we shouldn't have them in the repository, I guess. Yeah, so that seems to be working very nicely. I think it looks great. Yeah. That was very short, yeah. It's 10 seconds, so they run for 10 seconds each, and then they rotate through, I think. This is very cool. Yeah, I like it. Okay. That's an improvement. So one thing I also want to add, and I got a request for that from a friend of mine, is to add max headroom GIF animation to the whole rotation of animation. So that needs to happen. I hope we can also add some other effects, but definitely the frame rate improvement is a good step forward. We cleaned up the shader toy stuff, and all we need to do now, I have to also update the Square Wave matrix server animations and that software, but I have to figure out why it is not compiling for me at the moment. So that is interesting, but I will probably do that off stream. So yeah, I hope that was interesting for you. This was a little bit of a demo of the cube and a little bit work on the FPGA. And yeah, you can do all of these things directly on the Raspberry Pi in the cube. So if you have a cube like this, you can synthesize the bit stream directly on there. It's not very fast though, but it works. It definitely is workable. I just prefer to synthesize on my computer and then just SCP it over, but you don't have to. It makes it really nice to develop stuff for this. I'm really looking forward to, that's another thing I really want to do, is hook up the IMU inside the cube to make the animations responsive. I saw that on the Square Wave LED cubes, where you could move the cube and the particles were reacting to the movement of the cube itself. That was really cool. So we might look into that a little bit during the stream, maybe not, we will see. I just don't want to do too much of boring stuff on the stream. So yeah. Okay, so to wrap up, I would like also to make a little bit of an update regarding the other projects that we are doing here. So as you might have seen, the other stream that we did were for the for Twang, the one-dimensional dungeon game that we are working on. This is I'm porting essentially Twang from Arduino to the iCEBreaker. We're porting a lot of the Python, and I didn't make between the streams any progress on the Python itself, on the porting part of things, but thanks to Zobs or Sean Cross, we managed to get LiteX running on the iCEBreaker, which is pretty huge. So LiteX is the SoC generator that we will be using. Let me just switch over to the face here. So why is it not showing desktop? It would be nice to just see the desktop. Maybe let's do this. Yeah, let's do that. Yeah. And we can watch the cube animate. Let's run the cycle while I'm jabbering. Okay, so thanks to Sean, we got LiteX running. LiteX is the SoC synthesis framework that we will be using to run the Twang compiled stuff on the iCEBreaker. So I got it to work. Now I want to also figure out how to write just simple C code for it, and then we can try to get MicroPython running on this. So I have to see which things make most sense to do on stream. We will get back to a little bit of Python coding on stream, but usually I feel it is better to break it up a little bit. So we might on the next stream do some hardware assembly or some hardware fixing. So for example, I have a bunch of Blackmagic probes that failed QA. We could fix some of those, or iCEBreakers that failed QA that we can also look into and fix on stream. That might be interesting, how I approach hardware fixes like we did for the Glasgow. We could also do some, there are also assembly stuff we can do. So if you maybe saw, Sylvain also got some of these boards. Let me switch on the microscope. This is not even fitting in the screen. So this, let me switch to the microscope. Let's do this. So what this is, it's a HyperRAM, quad HyperRAM PMOD. So you have 4 HyperRAM chips on one board that you have chip selects to address with. So is that better? Yeah. So I ordered these from Oshpark. They're even in here. You see they're length matched, the traces for the data and address. So yeah, we need to assemble some of these prototypes. So we could do that on stream. That might be interesting. And so I'm trying to break up things regarding the streams to make them a little bit varied. I am trying to stream once during the week and once during the weekend. So I hope I will stay with that schedule. Usually around 2 p.m. Pacific time. I'm not exactly sure on which day though, because things are always changing a lot and I have many other things that are happening. But I am slowly converging on a schedule. This hopefully eventually we will get to a point where I can set, it's like, okay, this day of the week we are streaming from 2 p.m. and this day on the weekend we are streaming from 2 p.m. So I'm slowly getting to that stage where I hopefully can announce this. But for now, just subscribe, follow me on Twitter, follow me, go to the Discord server, join the Discord server. I will be announcing the streams on there, as well as if I make progress in between the streams, I will definitely let you people know. yeah, otherwise, thank you very much all the Patreons that are supporting me. This is so the people that really need a shout out is Edward Borden, Jerzy Hacker, Jordi Parky Rodriguez, and Sid Price that are supporting on Patreon. This makes the streams definitely possible, and they add to the motivation to do these. And allow me to invest money into improving the gear to show the streams. Yeah. And as the last thing, so we will, I think that would be it. Thank you very much, and have a wonderful day.